happy to be here today. This is an exciting event. As Martha said, I'm a newly appointed assistant professor, and I mostly work on display technology and camera technology. So in general, imaging. So imaging is pretty much everywhere, in space, in medical imaging, in the hospitals, in consumer devices, but probably the most promising new directions that we're working towards in both the displays and also the cameras are these personalized experiences. You can think about it as wearable displays, but what we really talk about here are the new user experiences, personalized experiences that are made possible by underlying technology that where the imaging device and the display device is part of the ecosystem, right? So we've seen a lot about wearable displays, skin conductance measurements, and other wearable devices, and these are all part of this ecosystem. But what's really important to think about in the future is these experiences that we're creating, and these should be personalized. So my group is the Computational Imaging Group. We work on new camera technologies, new display technologies, usually at the intersection of optics, electronics, and scientific computing. And we build new cameras and new displays, but with the goal of building new experiences. So I'm going to try to give you a flavor, a sense of what's coming next in this display-oriented world. Also in the imaging space. So for instance, recently we built this camera which creates a new modality that may eventually, hopefully, help with personalized experiences. Right now, we just built the camera. It's an experimental platform that allows us to capture totally different types of visual data, basically velocity. So we have here a reference frame from an RGB camera, and we built a camera that can capture the velocity of the objects on a per pixel way. So this isn't quite a personalized display yet, but we hope that it soon will be because it uses the exact same components as Microsoft Kinect and emerging cameras that are being integrated in personalized cameras right now. So that's just something that's going on in my group. But the core focus of this talk is actually on these emerging trends and applications of computational light field displays. And I've been working on this for a number of years. You can think about these as 3D displays, but over the years, I've become aware that not all applications of 3D displays are equally important, and people simply don't care too much about stereoscopic image display or 3D movies. But I'll try to convince you in the next 15 minutes or so that the same types of displays can actually create experiences that are very different than what we think about 3D displays today. So starting in about 2010, 2011, we've been working on these new and emerging types of displays that create better quality 3D experiences than anything you may know today. In particular, we built this display called the Tensor display. It uses a combination of different liquid crystal displays that are high speed. What it gives us is this 3D image of a scene where we can look at from different perspectives and see a high resolution 3D view of a scene. But the magic really comes in when we use a high-speed camera to show what's underneath are these high-speed patterns that are being displayed at all these different LCD panels that perceptually fuse into a consistent high-resolution view of this 3D scene. So we use advanced algorithms, new types of display electronics and optical configurations to create experiences that may not be obvious. And why am I talking about 3D displays? Because I think these are part of future displays and head-mounted displays and other types of displays that support new experiences, such as in virtual reality and augmented reality. We're usually looking at head-mounted displays like the Oculus Rift and things that resemble a form factor of the device that you can see on the right. This is something we built in the lab over the last couple of months, and what that provides you is an experience that you don't get with any virtual reality display today. What it basically does is it shows you a stereoscopic image pair, just like any 3D display, but it also provides these natural focus cues that we can see in the real world, but that aren't supported in any display today. And eventually, I want to show you that supporting these focus cues actually enables totally unconventional display modes, such as personalized displays that correct for the visual aberrations in your eyes as well. So instead of allowing your eyes to naturally focus at different places in space outside the physical device, these could basically put the glasses into the display, and you can dial in your prescription and software so that you can correct for personalized aberrations, different types of aberrations that even differ between the different eyes in the display itself. And all of that is based on the same fundamental technology, which is light field displays. So here's a prototype display that we built last year. It's basically just a cell phone that we kind of hacked by adding a really smart algorithm into it and kind of modifying the hardware by adding this transparency mask that has a special code in it. So if you see the modified image and observe it through this mask, it appears to be in focus, even though the camera in this case isn't focused on the screen, right? So it simulates this viewing experience where a person isn't wearing their glasses and can't focus on the screen, but you still get to see a sharp image. So let's take a step back and think about what's a light field display in general. Here it's depicted as a television type display where three friends are watching a movie, and what they see is different perspectives of this virtual scene. Each person gets to see a different perspective of the scene, two different images with their eyes, but without the need for wearing glasses. So that's the core idea here. We have a glasses-free 3D display, if you want. And in order to achieve this, the display has to emit all these different perspectives of the same scene into different directions. And normally, when we talk about glasses-free 3D, we see two different images with our two eyes. But when we think about focus cues, correcting visual aberrations, we actually have to get multiple different images into the same pupil, right? So that's very, very challenging to do technologically, but it's the same idea. So the display emits all these different views, normally over a wide field of view, sometimes just over the pupil of the eye, but that allows you to create these personalized experiences. It's actually very challenging because what we really want is emit hundreds of different views to an audience like you so that every pair of eyes gets to see two different images, right? So we need to emit thousands of different views from a screen like this in order to achieve this. So that's extremely challenging electronically, optically, but also the amount of data that you need to process is very, very challenging. So 100 by 100 views with HD resolution streamed at 60 hertz, that's terabytes of raw data that we need to be able to process per second. So the approach that we're taking is this computational display, compressive display approach, where we design algorithms together with the display optics and electronics to enable these experiences, bring down the data rate, make it manageable with hardware that we have today. So light field displays are actually an old technology. They've been around for the last 100 years or so. You may have seen this in these Cracker Jack kind of wiggly postcards, bookmarks, and so on. Usually there are two fundamental technologies that are still being used today. Parallax barriers, where you mount a barrier mask with a couple of pinholes in front of a 2D screen. And when you walk around the display, you see through these pinholes, and for every perspective, you get to see a different subset of the pixels on the screen. So the problem with this is that it's very low resolution, because if you want 100 views, the resolution of each view will be 100 times lower than that of the panel. It's also very dim because you block most of the light. So Gabriel Lippmann, who also invented color photography, invented a technique called integral imaging, where he mounts small arrays of lenses onto conventional 2D displays. I mean, he used film plates back then, but the idea is basically the same. You multiplex these different views next to each other on a conventional display so that you get to see two different perspectives. So all of these support a few depth cues of the human visual system. And the most dominant one is this binocular disparity, at least when you think about 3D perception with two eyes. And binocular disparity just means that you get to see two different perspectives of the scene, one with each eye. Coupled to that is an oculomotor process that's known as convergence. So the eyeballs in the sockets actually physically rotate. So it's a muscular cue that tells your brain how far away a scene is. You can also move your head around a scene and get to see different perspectives. And the final one is accommodation and blur. So you have a lens in your eye that actually focuses on different distances, usually coupled in both eyes. But if there are aberrations in there, that's why we need glasses to correct for those. If you think about stereoscopic displays today, they only support a few of these depth cues, so they create visual discomfort and other problems. So we work on these displays that support all these different depth cues. And if we have devices that support all these depth cues, we can also enable new experiences, like vision correction, focus cues for virtual reality, and in general, just provide better and more visually comfortable experiences. So the goal is very similar to what people in the 70s and 80s and 90s have done with holography, but using practical technology that's available today. So I just wanted to show you one of the prototypes we built in 2012, this Tensor display. It's basically 3 stacked LCD displays. If you rip them out of your screen, they're actually transparent. So we use 3 of them with a single backlight behind them. And then our contribution is really on the algorithmic side. And I'll spare you the technical details. But the idea is that we start with a 3D scene, for instance, a couple of bunnies that are all at different depths. And then we run a non-negative tensor factorizations implemented on the GPU to compute a set of patterns for each of these LCD panels that change very quickly over time so that you perceptually average over all of these. And when they're optically overlaid, what you see is an illusion of this high-resolution 3D object floating in space. So it's something totally different from what people have done in the past. And the reason why we can do that today is because we have computers that can crunch numbers very fast. So again, here's what you kind of see recorded with a camera with an exposure time that approximately corresponds to the critical flicker fusion, the human visual system. But when we use a high-speed camera that's much faster than the human visual system, we can see these patterns that flicker around. So the basic message is that you don't have to show what you see. You have to show something that will be perceived as what you want. So all of this works well with compressible data. So it uses ideas that we use in JPEG image compression every day, where there's a lot of redundancy in this data, and we want to exploit that computationally. We started a blog called displayblogs.org to publish all the hardware instructions and software so other people can actually pick up on this. And there's commercial efforts now too. A lot of large consumer electronics companies are picking up on this. And hopefully soon we'll see something on the market. What we've been focusing on more are these wearable displays. For example, near-eye light field displays that you can use for augmented reality and virtual reality. And here the problem is really that these focus cues are not supported. So in the real world, we have these 2 different eyes, and let's say we want to look at an object like the teapot. What happens is that the lenses in our eyes will accommodate to that distance so that it's in focus on our retina. At the same time, the eyeballs will rotate in their sockets to verge on the same distance. So everything's happy because all these cues are the same. If you move the object, both cues will change. Your eyes will still focus on this teapot, and the vergence will be changed accordingly. Now, when we use new and emerging displays, like immersive head-mounted displays, we present 2 different images for these eyes. But our eyes always focus on this virtual plane of the screen, of the LCD screen, and that's at a fixed distance. So as soon as we move this virtual object away from the screen, our eyeballs will rotate, so they verge at the right distance, but the eyes are still focused on the screen. And this mismatch between the focus cues and the vergence cues creates visual discomfort. So that's something that we're trying to solve with light field displays. So we built this display. Looks very much like an Oculus Rift in this case, but we have multiple LCDs in the screen. They're all put together in a form factor that resembles the Oculus Rift. And then we apply these light field factorization techniques to compute the patterns that are actually being shown on the LCDs so that when you look at it, you can naturally focus your eyes. In this case, you can see on the right, the camera is focused on the front of the temple and the back is out of focus. Or you can just focus your eyes on the back and the front will be out of focus. So this is what you would naturally see, which is not supported by any display today. So that's hopefully something that you'll see in the consumer electronics world soon. And these are all tools that we use as a medium, right? What's the medium? The medium includes not only the content, but also the devices that deliver the message. Right? So here we just see some preliminary shots we filmed of our prototype. We just manually focus the cameras on different parts of the scene. And we can continuously do that. This is particularly important for younger people and for objects that are close by. So things we interact with in a personalized space, things we can grasp, because these accommodative cues are most important for everything that's closer than about 1.5 meters. So anything that's close to you, that's where this matters the most. I'm just going to fast forward a little bit. So now, one of the big questions of these technological developments is how do we actually create content for this other than games? Because we want to use it for education, we want to use it for entertainment, but we also want to create this presence in places that we normally can't travel to. So we tested an emerging camera technology called light field photography, where we captured the photographs of the real world that are suitable to be directly streamed and provide these focus cues as well. So if you take a normal picture of a scene, the focus cues are lost as well in the camera. So in this case, you can see a photograph that we took on campus with this light field camera, basically directly record the light field, put it on the display, and present this end-to-end pipeline of creating real content, streaming it on these emerging devices. But as I mentioned earlier, we can also use the same kind of a technology to create very personalized experiences. Right? Think about personalized displays today. They give us recommendations for restaurants that we may like. They give us recommendations for music. We can select that on our screen. But what if you take this personalization one step further, where it actually shows us an image that only makes sense for us, because we have particular viewing preferences. We may have particular conditions that other people don't have. So can we build devices that support this kind of stuff? And the answer is yes. Using light fields, we can create displays that basically show a 2D image outside the physical device within our accommodation range, and thereby integrating the glasses into the screen itself. And that's important because a lot of people have hyperopia, myopia. As we get older, we have presbyopia. So these kinds of visual aberrations get more and more complex, and they also get more difficult to be corrected for with glasses. For instance, 40% of the US population is reported to have myopia. And in some Asian countries, that's even larger. When you think about driving experiences, you don't want to switch contexts all the time. What if you forgot your glasses, and so on? So we've been very successful for thousands of years to correct for these aberrations using glasses. And that works really well. Same with contact lenses or surgery. But all of these are intrusive approaches where we either have to wear something additionally on our head or undergo surgery, which may not be optimal. So encoding these experiences into the digital world is, I think, what will help us when we interact with these devices, or with digital devices in general. So the prototype I showed you earlier is basically a modified iPod Touch, where we just added this transparency mask that has a couple of pinholes. There's a parallax barrier I showed you earlier. And the experiment we did was using this camera that's actually focused very far away from the physical device. You can see that on the right, where the battery is totally out of focus, but the image still appears to be sharp. Right? So the reason we can achieve this is by putting the intelligence into the device itself, and it knows what your prescription is and where you're looking at from the screen. So again, the result looks something like this, where we run all this computation to compute a pattern like this. Right? Normally, you can't read the font, you can't read the buttons, but when you show this special image and observe it through this particular mask, it appears to be floating outside the physical device in focus. And so that's something that I'm really excited about, creating these personalized experiences that may transcend what you think about personalized experiences now. It doesn't just track your preferences and runs machine learning techniques to recommend restaurants and other things that you can do in the physical world, but it also gives you a very particular experience when you interact with the digital world. What's really interesting here, at least intellectually, is also looking at these higher order aberrations. So people who get LASIK surgery oftentimes have dominant higher order aberrations after that are very different from the aberrations you see in cameras. And it turns out we can correct for these also, which is great. You can see that on the bottom. So we really hope to make an impact on people's lives by building technologies like this. At least this was a conceptually study that it's possible to do this, and it could be integrated in all these existing technologies like e-readers, displays in the car, in your phone, or even remove the eye strain of surgeons. So I don't know if you know the Da Vinci surgical system is this robotical surgery system. I mean, it's based on virtual reality. The surgeon actually looks into this big box. He doesn't see the patient directly, but he can do minimally invasive surgery using these robotic arms. That is much preferred to, in some cases, to traditional surgery. And all of that relies on the surgeon to actually, see images that are being streamed live from these robotic arms that have cameras integrated. So if we can create better and more visually comfortable experiences also for surgeons, I mean, that would be great. So again, I'm running the computational imaging group here at Stanford. We build cameras and displays of the future by basically bringing the intelligence and putting it algorithmically into these devices. So with this, I'd like to thank you for your attention, and I'm open for any questions you may have.